YouTube and it wasn't coming up. But my name is Cody Rogers, and today we're just gonna do another set of circuits. This circuit you might be familiar with if you watched my previous live stream from last week. Um, it is well. First, since nobody is here yet, I do like beer, and I've started drinking one beer during each live stream. I'm gonna just introduce this one, which it is a vanilla porter from Churchill Brewing Company in Saskatoon. It's very nice. I liked it a lot, or I like it a lot. I still have a little bit left in my growler. But anyways, we're gonna do this circuit here, and that is the triangle wave oscillator. Now, I was having quite a hard time describing it last time, even though I have like sort of described it before, and it is easy to describe with our golden rules when we think of them. And remember, in this setup, we're always dealing with what's it called? Perfect op amps. There are imperfect op amps, and well, there are only imperfect op amps. There is no perfect op amps, but in the simulation, we only ever use perfect op amps. So we will be using these ones, and our golden rules are that no current flows into the inputs, and no there is no voltage offset here. So this is the same. So that means that since this is at ground, that means that this also wants to be at ground. It's not necessarily at ground, but it wants to be at ground. So how do we get a triangle wave here? So you can see this test point right here will be a triangle wave. That the way we get to that is that if we think at exactly 1 volt here, we'll yeah, I think I'll come to the capacitor later. That's basically an integrator, so it's changing the like it's what's output in the triangle waves because it's given a constant voltage, and then it's integrating the constant, which of course is a uh, straight line going up or down. Hmm. Sorry, my screen went out. There we go. So now, when this is at 1 volt, that means that about a half milliamp will be going through the 2 kilo ohm resistor, and that means a half milliamp has to go through the 10 kilo ohm resistor, which results in 5 volts. Now, if when this goes up just past 1 volt, let's say 1.1 volt, it won't get that far, but let's just say it does. That means that this will be putting forth something more than a half milliamp. So that means that this will want to have more than 5 volts going across it. To make it not have that, that means that we will start having a negative voltage here, which then this will start shoving the output down because it's the non-inverted input until such time that these two are equal again, and it will never get that way until when this goes to -5 volts. That means that this one over here, so we're going to slowly charge this up, and well, it will charge. Well, it's going to be switching its voltage. And then as it goes -5 volts there, it's going over there. That means we're going to have a minus 5 volts here. And then this will be outputting Yeah, so we got a volt coming up here. So that's plus. Yeah, so then there must be the minus 5 volts here. Well, it will get to a minus volt, and then this will switch again to be plus 5 volts. Let's just see if that happens. And see, we're going. Oh wait, yeah. Sorry, it had already switched. That's why. Here, I'll just stop this again. So, yeah. So this is when it just switched. It was not quite at one, or it was just over 1 volt. Then it switched, so now it's outputting 5 volts. Sorry, that made more sense. Now it's gonna go all the way down. This is gonna be outputting 5 volts. So now this will start changing. It will go from 1 volt here. See, right now it's at almost 1 volt, and it's gonna go down to just over minus 1 volt when this is at minus 1 volt. That means that a half milliamp is gonna be flowing this way. Now, when it's just over minus 1 volt, that means something just or when it's just under minus 1 volt, that means something just under minus a half milliamp will be flowing this way out of it, and that will cause a positive voltage to have to be here, because yeah, we will want a larger voltage drop across this 10K, and that's going to again change the voltage to there. Let's go. And we're gonna go down, 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 down. We're gonna hit minus 1 volt, and then it goes to minus 5 volts. So I think I finally got that circuit. If anybody had any questions or comments about the circuit, that'd be great. I'm gonna cross it off finally, and might as well go to the last circuit that I had listed on to talk about through the Art of Electronics. 4.89 on page 276. Yeah. Yeah, that took a long time for me to really get straight in my head. I really do like talking like this, like having these streams for this reason. It's really good for my personal learning. Stock node tracer, what? Okay, this one might be a little bit funky too. I'm gonna just stop this. Then we're going to go to active building blocks. Minus top. Yeah. What is this? Open supply by the batteries. I think we're gonna do a different one, because that one doesn't seem. Oh, oops. Right. What we're gonna do. Close this textbook up. I want to show a circuit that I found online, actually. This one right here. So, I know this seems like a very simple circuit, but actually, just want to show it right here before I go. I'll do a couple on this one, but it I spent like a lot of time making a circuit that's also found in Art of Electronics, a little bit edited, to make an LED driver sort of like this, but mine is way more complex. So I just want to see if this works the way that I think it does, and I don't know why I didn't do it before. It makes no sense. So let's draw the resistor, and then we need to draw a active component, transistor P&P right there, and then we need to draw resistor and draw components. Oh, I think it put it in out. I don't know why they put it in output and labels there. It's not a. It is an active component per se. Like it's, um, but whatever. There we go. Draw. Add wire. Let's add a voltage source to terminal. We'll make it just like there. Oops. Want to go like that. Now we will draw all the wires in. And right there, 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 there. Oop, made a mistake here. Clean that up there. Because we need to draw these wires in so they all connect. Or else it won't, won't do anything. Voltage source 5 volts. This is going to be the LED. I want to see, can I red value, max, brightness, current. Okay. So I think that red value, it means that it will burn up a volt there. So if it's going to go, we have 5 volts applied here. We say we have 1.2 volts here. Like 2 diode drops. So that means we would have 3.8 volts, say 4 volts. So no wait, but then we have a volt passed over there. That means 3 volts. So we should have about, well, we would have about 4 volts here. So that means whenever there is more than 4 volts right here, this will be on, and otherwise it will be off, if I'm understanding it right. I think that's what they're getting at with the circuit. So that means that right now, this would be 2.5 volts, so nothing should be happening when we do it. Let's try that. And of course, I'm wrong. 4.972, 5 volts. Here, let's move that out. I am going to, yeah, I got something completely wrong there. Now I'm just sort of floundering. See, yeah, yeah. So, yeah, that's, now if we increase this to 10K, I think I'm understanding this one better. Okay. Okay, now we have what I expected. Sorry about that. So now, because this, so right here, it has a very small voltage there. And so let's see, we got 5 volts here. So if we wanted, yeah, let's change this to 4K. I think will be the turn on point. So you see we're still not quite there. Now I bet if I lowered this to 3K, no, still not. Yeah, so we got, oh yeah, because we would have to have about a milliamp at least, I would say. Go 1.5K. Yeah, see, now we're slowly turning it on. Edit. Go 1K. See, now it's on. Then we go down to say 500 ohms. Apply. Yeah. So now it's on more properly. That was actually the next one down here. NPN. They put the light on the other side. Let's read what they said. So we on off. V1 on / off. 0.73 volts over 0.02 volts. So when this is really, really small, then this is off. When it's really, really high, like this one, then it's on. So it's basically the opposite of this. Let's go here. So yeah, we got that. Wonder which one they're using. Doesn't really say. Let's go to, yeah, and now it's really on. Yeah. We'll edit this and we'll go to 1. Apply. Yeah, so see now that's basically how that one works, I guess, is that this. So let me just we'll go back to thinking about currents with transistors. In a current, like, so for transistors, it's all mostly determined via currents. So now this will drop 0.6 volts. I see, that's one diode drop. That's what it's going on here. The V on, yeah, V1 on is whenever that drops more than a diode drop, it will be on because not as much current will flow through it. When, like right now, we have something that's a very, very short, it's a very, very low resistance, that means that all the current will want to flow through this way because it's the path of least resistance, whereas flowing this way would be more resistant. So let's, because yeah, you see here we drop a half or a 5 millivolts. Go to 100. I wonder if I can suppose where it would be. So I think that if I change this to say, I don't know, 4K, we would want, yeah, let's go for this, change this to 4. Here, I'm gonna stop this. I'm gonna change this to 4.3. Okay. And I'm gonna change this to 700. And I think it will just turn on at this point. Let's see. Yeah. So I am basically right. That is very nice. Now, let's lower this 600 and it should turn off. Nah, not quite. It just dimmed. Probably have to go a bit longer. There. Now it's off. Now let's see if we go back to that 600. I wonder if it will turn back on. Yeah, it does. And if we go to, say, 1,000, yeah, it's on. So that is interesting, I find. Let's see if there's other ones. I just found those two. And I guess, so for my application that I did, I guess these circuits actually wouldn't be what I want. Because, well, here, I can show you what I did. It's still a little bit more, open file. It's a bit more than I actually needed to do. Because I think I'm gonna use a comparator. Now I'm actually working on that right now. But go dusk to dawn. Did I not put it in? Part 2 project. Ah, here we go. So you see, this is what I mean. It's a lot more complex than the circuit you just seen, but it is much better at turning it on and off, for one thing. Like, let's now change this, and this will change exactly at 30K. So I'll go to 29K, apply, okay. And you see this LED, we're focusing in on this LED. I'm sorry, it is such a big circuit, it's hard to see things. But you see it's off still. Now, we'll go to, well, let's just, to prove a point, go 29.9K. Apply. See, it's still off. I can go, yeah, I know I'm getting a bit overkill here. Oh, now it rounded to, okay, let's go there. Okay. Well, it's still rounded. Well, there. 29.9. Wonder if I can go 99 though. Can I do 99? No, rounds it up. Okay, but anyways, you get the point that basically this one will stay off and then it will turn on. And it turns on with that, with this, like, one milliamp the whole time. So now, like, it's no, like, see, I can change this to 150K. Apply. Okay. And it barely changed. Like, it went from, what was it at? 990 microamps, and it went to 1.1 milliamp. So it's basically, it is exactly at the current amount that I set it at. Whereas in that other circuit, as you saw, it would vary based, like, very wildly on what you were comparing, like that one resistor was. So this circuit I actually still like better. I am gonna be doing one that just uses a comparator, which you, I think, probably not this Monday. Well, it might be this Monday. I don't know. I missed a week of releasing my regular videos. I was gonna release my power supply update video where I added a linear regulator, but I didn't do that. So I'm gonna either do that, like, I might do that tomorrow, just release it right tomorrow, or I might just go back to the regular schedule and release it Monday, and then the new Dusk to Dawn one will also be released Monday. Let's just go down. Schmidt trigger inverter circuit. Let's do this timer one, because we can actually do in the Fallstack simulator, you can do the 555 timer. So new blank circuit. Draw. digital chips. Oh, here, analog hybrid chips. There we go. So now we got the 555. Oh, oops. I just want one of you. Cancel. Cancel. Delete. I just want one of you. So now, here, I'm just gonna pop this out into another screen. Just because to construct it here. Draw, add resistor. Yeah, I think this number 7 is the discharge pin. For those of you who haven't used a 555 timer before, basically what it does is it can either, well, it can keep time for you. Like you can set it so that it will, oh yeah, passives. It will create a, it's the best way to put it, like a pulse for you. So like you could input a pulse and then it will output another pulse. And that's one way that you can use it. The other thing, you could make like a sort of oscillation. So I used it in conjunction. I made a just a buzzer, and it just buzzed. And made my one coworker very angry with me. He was the guinea pig. It just buzzed every 8 minutes. So what I did was that I had a very slow timer go on with this, so it would oscillate every 7 minutes, and it would output that, and then it was connected to another timer that would oscillate very fast and make an annoying buzzing sound for 1 second as the first timer was output in high. Yeah, so that was a very fun circuit to do. It made my one coworker very angry with me, which was very like, I found that was very nice and happy. Made me happy. No, he didn't. He's one of those people. He also does a lot of pranks. So the way I usually say it is that if you do pranks, you have to be ready to have pranks done on you. Of which that happens to me sometimes. So I think we got. Why does it have more? 1, 2, 3, 5, 6. Ah, yeah, we have to have this one there. Is that the control pin? 1, 2, 3, 4. Yeah, so they didn't do anything with the control pin. We do have to put the reset pin up here. Now we will see if I remember. I'm actually going to clean this up. I'm sorry. If I remember how this chip works. Here we go. There we go. So now you see it's outputted 5 volts. I'm just gonna put this into the scope. So, oh, that's the other thing I forgot to do. We have to, it's very important to change these because they dictate basically everything. So now edit 105, okay, apply, okay, go edit 2.2 U, okay. So now that we have that assembled, let's double check it. they put in 9 volts. We don't necessarily have to do that. So now, what this will do is that while it's in the charging mode, this discharge pin doesn't accept any current. Basically, it's basically an open circuit here. Pretend the discharge pin's disconnected like this, while this is charging, and that means the output is also not is at 0 volts. So when this is disconnected, the output's at 0 volts. Now, so it's going to charge this capacitor, which will change the voltages at the trigger and the threshold. Now, I always get these mixed up, so I might get them mixed up again here. But so this will charge this capacitor, which will change these two. When one of these two, let's say it's the trigger pin, because that makes sense to me, that it would be the trigger pin. When the trigger pin gets up to 2/3 of 5 volts, so basically, no, well, we're going to make this easy. Oh, wait, cancel. We're at, that's the trigger pin. We're going to make this easy. We're going to put this as 6 volts. So when this trigger pin gets up to 4 volts, then this is going to go to high, like it is now. And the discharge pin is going to switch to low, so it's going to start sinking. What that means is that this capacitor will start discharging just through the mega ohm resistor. And it's going to discharge until the threshold pin hits 2 volts. So 1/3 of the VCC voltage. Now, we could do the calculation to figure out what those times are, but it involves decimals, and I really like these chats or these streams to not involve complicated calculations. Not that it's complicated, but I like just being able to talk with words about circuits. I wouldn't be able to do that with this one. So we're just gonna run it now. You see, it's at 6 volts. This is 6. It's all at 6 volts. Why is that? I think I did something wrong. Reset. What did I do wrong? No, that's right. Let me see. 555. Here, I'm gonna just bring this back into the thing. 555 timer. In out. So we got ground is 1. It's right there. Go here. There's 1. Okay, good. Trigger is 2. Threshold is 6. Yeah, 6 and 2. Good. Discharge is 7. Yeah, that's good. Power supply is 8. Reset is 4. What is happening? Like, I think the circuit's right. Just want me to take that control voltage to... Yeah, that's not right there. What happens if I take this one to ground? Nothing. I'm sorry, I'm just exploring this. Still open it. Too bad connections. You know, I think I'm going to move on from this one. Doesn't make any sense to me why it isn't working. Oh, I think I know why. Add ground. There we go. We didn't have a ground. So let's ramp up the simulation speed here. Yeah, so now we are doing it. It is correct. So now this is going to go up to 4 volts. No, I was wrong, I guess. It's a lower one. So this will go up to 4 volts, and then this will change to 0 volts. And then this will start sinking. So let's just see if that happens. Then we hit 4 volts, and now it's at 0 volts. This is sinking current, so it's dragging the current over. You can see. And this is going to go down till it hits 2 volts, and then it's going to go back to 6 volts. This is going to start charging again up to 4 volts. Whew! Sorry about that. That was, yeah, well, one, I got the behavior a little bit mixed up, but it really wasn't doing what it was supposed to, because somebody forgot to put in the ground, which I have an electrician friend who told me once that it is always the ground. Yeah, that's what you should always look for, is the ground. Yeah, so thank you for your patience. If anybody has any questions during the stream, they feel free to ask. I know I usually just, freestyle in here, but I'm always open to questions. I'd love to have people suggest circuits if they wanted. But let's go. Now, I'll do that later if I have time. We will first. We're gonna just delete that. Actually, I wonder if they have that here. Digital miscellaneous devices. No. Power converters. Op amps. There. This one. Yeah, they have a few different ones. There's the internals of it. Oh, that's pretty cool. This is the internals of the 555 timer. Anyways, I guess I'm going to move on because this isn't really exactly what this it is all about, but it is a very nice, like, look at that. That's pretty cool. Let's go. I'm going to go into my basic engineered circuit analysis book and do, well, let's do figure E4.1 on page 159. It's another op-amp circuit. I think the reason I picked, oh no, wait, that's the other one. Yeah, we'll do this one first, though. It is, okay, we'll go file, do blank circuit, active building blocks, the plus on top, and let's just draw in this circuit. But yeah, for those of you who do like these live streams, I guess it'd be nice to know, like, just please, like, tell me what you like, what you don't like. Then I don't know, I might change things up a bit based on that. Um, what I'm doing it for, like, I think I've said that multiple times, is I just like to be able to talk about circuits and verbalize my thoughts about them, because I think that it really helps my own personal understanding and what's that HR word term, like, being able to talk to people well. HR people like that are supposed to be good at that, but yeah, and that improves my skills in that respect too. So I think that I gain a lot from doing it, but I would like to know what you all gain from it too, because there's a lot of things I could be doing during these live streams. Like, I've often refrained actually from talking about uh, history sometimes, because I like history, but I figured that I could talk about that at other times. But right here probably is the greatest place to talk about it. Unless you think it is. Then I might change my tune. I might just, whenever I'm constructing these circuits, instead of babbling like I am now, I might babble about Julius Caesar or Alexander the Great. This might be fun. Or I might babble like about beer. I don't know if that makes people uncomfortable, or like they don't like the beer aspect of it. Like, I just like drinking beer. Sometimes I like good beer, so um, and I just did it. It's a good way to know when to stop too. Guess it's like that saying from Steve Jobs, who said that a meeting, if those in the meeting can't share one pizza, then there's too many people. If the live stream goes for longer than one beer, then it's too long. So this circuit here, basically, we're going to apply, so they want to apply 12 volts here, so we'll do that too. We'll apply 12 volts, apply, okay. So now we're going to apply 12 volts to there. That means that this will also want to be 12 volts. So, to be 12 volts, that means right here's 12 volts, so we're going to drop 12 volts across this 2 kilo ohm resistor. That means we're going to have 6 milliamps traveling down there. So then we'll have 6 milliamps traveling here. So that means we will have A lot. Yeah, because we're gonna have 60. That is a high amount of voltage. They can't possibly be wanting that much voltage. But yeah, that is what it would be because it is a yeah. So that would be basically 60 and 72 volts there. We're gonna have to change this. Just go. This is a weird textbook. This isn't art electronics. This is basically engineering circuit analysis. And I find that some of those textbooks, they are overly academic-y, and this is one of them. I find it just like why would they say that? Um, so 72 volts is going there, and this 10K, that would be 7.2 milliamps. They're saying 8.4. Because that's the question in the textbook, is what would be the current going down here. So let's actually, since that's the question, we can add in an ammeter. Put some labels, add ammeter. There. Now let's run. So it is 8.4. Ah, yes. Yes, I see where I went wrong. That is right. It's because, so, yeah, there's, so we'd have to have 12 volts here. So that means that 72 volts, as I said, like, since 12 volts is here, that means 6 milliamps would be going down here. So that means 6 times 12K, or 6 milliamps times 12K ohms means that we have 72 volts there, which means 12 plus 72 equals 84. So 84 volts being dropped here, and then that turns out to be 8.4 milliamps. Yeah, that makes sense now. Sorry, I didn't remember that some of that part. But one thing I'd just like to say, like, this seems like a very odd circuit. I don't know if it would happen in the real world very often, but whatever. Let's go. I want to try something. 2.56 on page 75. .56. Yeah. So this was one. Okay, new blank circuit. Let's see if I can draw up a current source quickly. This isn't the actual circuit we are going to be, because it's just like, see, inputs and sources. You see here we don't have a current source. Actually, you know what we could do? We can probably just take it from here. Transistors, emitter follower, current mirror. There we go. We don't need all this fancy stuff. So you see this basically sets it there, so whatever we put in here, we'll have that 7.2 milliamps, you see? This one just can up it. So we can delete that, 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 and that. So what I want to, what do I need? It says I need 12 milliamps. So, edit this, go to 300, say, edit. I guess I could do the math, but get nope. Let's do there. That's good enough. So now we are going to stop it there. Delete this here because what it called for is a current source. So I'm just gonna, give it a current source. Before I sort of skipped these ones because I was like, well, there's no current source in Volstat Simulator. But this way, there is of sorts. Yeah, and then there we go. Now we'll draw this, add resistor, then right there. Okay. 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 Edit. 4. Okay. Apply okay. Now I'm just gonna absolutely fail at analyzing this. Yeah, so we know that this will be about 11.7. We are going to connect all these here. It's like that, that, and all this is going to get connected. So we're going to have 11.7 milliamps going through there. And it wants us to find current going through this 4 kilo ohm. Oops. So what we'll do, like how we usually do it, is we will draw a label at ammeter right there. So now we got an ammeter there. So we have 11.7, say they're 12 or 10 milliamps or whatever. Going through there, we have to figure out what the overall voltage, I think, is going across. Would be the best way. So we got 4 kilo ohms, 12 kilo ohms. That means that, what would it be? 3 times as much current would be going through here. But first, we should figure out this. So 4 kilo ohms and 12 kilo ohms. The 8 kilo ohms is in between them. So this will be about 8 kilo ohms here. I'm just doing some rough math. So that means 11 kilo ohms here. Say this is all 12 kilo ohms. Just to try and get this math over with quicker. So that means we want the one in between 12 kilo ohms and 6 kilo ohms. So that's about 9 kilo ohms in total. Let's estimate this current at 10 milliamps. 9 times 9 kilo 9 milliamps times 9 milliamps times, or not 10 milliamps times 9 kilo ohms. Sorry. Or now let's go with 12. So 9 times 12 is 90, and then 18, 108 volts. That seems very high. Again, cancel. I bet this is gonna fail here. Yeah, because it can't keep up. So oh, I swear. Like I said, some of those academic stuff. So 150 times, so that would be 20, and then 10, 30. So that means we want 30 times 27. So 3 times 27, that's 54. And then 61, 81. So 81. Apply. Nope. Too much. Apply. So we will go with apply. Nope. I'm just trying to get to the right voltage now again. Oops, wrong way. 9K, go 11K. I'm sorry this one's taking a bit long. Again, some of the academic-y ones. Like, really, in what case are you gonna have 100 and what was it? That's 36 volts there. Okay, 36 volts. Yeah, 148 volts. Okay. So if we have 36 volts there, that means that 36 volts would have to be dropped here. So we got 8K here. 8K, that's 3K, 11K. So that means about twice as much will be going through here. So one of it will be going through there. And we got 12 milliamps. So that can't be right. What goes through here? 1.54. Yeah, so half of it, half and half. I think I'm doing this wrong. Quickly estimate in parallel. This is really embarrassing that I got this wrong. So boom. Yeah, so if you have 3 resistors, 10, 12, and 15 ohms, the quick estimate would be average of the smallest resistance, 10 ohms divided by 3.3 ohms approximately. Yeah, so that's what I did wrong. Yeah. Because, yeah, this would be 4 times, so that's 48 divided by 16. It's 3. Yeah. Yeah, that's what I did wrong. That was really silly of me, actually. I don't know where I had got that trick. Sometimes I do some weird things inside my head. But yeah, so this is 3 kilo ohms there. So that means that's 6 kilo ohms here. So that means that the overall resistance will be 3 kilo ohms. If you have 12 milliamps times 3 kilo ohms, that means 36 volts. So that's how we get to this 36 volts there. Now, that's going to be the same on both. So 3 kilo ohms will be passed here, 3 kilo ohms there. So half and half will go. So 6 milliamps through here. That means, again, I was right at this point at least, about 1/3 of that, or about 1/3 of that will go through here, and 2/3 of it will go through here. So I got that. But that was quite embarrassing that I got that one. I don't know why I was thinking that I could calculate the resistances that way. That was really silly of me. But anyways, it's good to learn these things. Then it makes hopefully them less common in the future. I think though we are at 9 p.m. So I think I am actually gonna end this broadcast unless anybody has any final thoughts or suggestions. I think I will just thank you all, and I hope you tune in to my next broadcast, which will be next Friday at around 8 p.m. as well.